today's class, we will study about electrical energy. So what is energy? Energy is the ability to do work, or it is the capacity to do work. Now, what is electrical energy? The energy associated with the motion of the charge. Let us consider a conductor. Let one end of this conductor is at a potential V1, the other end of the conductor is at a potential V2, such that V1 is greater than V2. Okay. Let there exist a steady current I, which can be written as I is equal to delta Q divided by delta T, where delta Q is the amount of charge flowing through the conductor in a time interval delta T, which means what will be delta Q is equal to I into delta T. Ready? This is the answer. Now, what is the potential difference between the ends of the conductor? Delta V. I think I can say this is V1 minus V2. V1 minus V2, because the direction of current you can see as it is from V1 to 2, which means V1 should be the greater potential compared to V2. Ready? So delta V is equal to V1 minus V2. Now the question I am asking is, what is the work done to move a charge delta Q from cross section 1 to cross section 2? Work done to move a charge from cross section 1 to cross section 2. Work done to move a charge from cross section 1 to cross section 2 is delta Q. If I am moving delta Q, if I send delta Q charge, from the previous chapter we have learned that work done is equal to delta Q into delta V, right? Delta Q into delta V. Let me take this potential difference is equal to V. Now, what is delta Q is equal to? I delta T. What is delta V is equal to? V. Which means we can say this is equal to VI delta T. This is the work done. If I say delta W, this is the work done in order to transfer a charge delta Q in a time interval delta T. Work done to transfer a charge delta Q in a time interval delta T. This is the work done by the external agency. Work done by the external agency in order to transfer a charge delta Q for a time interval delta T. Ready? Now the question, how these charges are moving inside a conductor. If it was a smooth path, like there were nothing else, just like the road on a Hartal day, where we accelerate a vehicle, what should have happened? The velocity would have increased. Velocity would have increased. That means this work done should appear as the increase in kinetic energy. Suppose the conductor was like a hollow tube or anything like that, and delta Q was a charge moving from one end of the conductor to the other end. That is the situation I am saying, that the work done by the external agency would have caused an increase in kinetic energy. Just like we push something. When something is pushed on a frictionless surface, it will start to move the velocity, because work done by the external agency, external forces, whether it is conservative, non-conservative, whatever forces we say, will result in the change of kinetic energy. That you have learned in first year with the chapter work, energy and power. Now this is work done by the external agency, and the formula is VI delta T already. But think the situation of a conductor. What we know? A conductor contains enormous number of charge carriers, such that the drifting motion is what is taking place. What is drifting motion? Motion involves an enormous number of collisions. Enormous number of collisions. Enormous. That is something to be noted. Enormous number of collisions will occur inside a conductor. as electrons drift from one end of the conductor to the other end of the conductor. Ready? As a result of these collisions, what will happen? Energy will be lost in the form of heat, and we have already learned that current I is equal to NEAVD, which means the electrons, the charge carriers are moving almost with a steady speed called drift speed. Charge carriers are moving inside a conductor with almost a steady speed called drift speed. That means there is no increase in kinetic energy. Inside a conductor, there is no increase in kinetic energy. Delta K is equal to 0. But there is a decrease in potential energy. As we move from cross section 1 to cross section 2, you can see that V1 is greater than V2, which means there is a decrease in potential. There is a decrease in potential energy. What should this account for? No change in kinetic energy, because inside a conductor, charges are flowing with a steady speed called drift speed. There is no change in kinetic energy, which means the work done by the external agency therefore must be dissipated as heat. Work done by the external agency therefore must dissipate as heat, which means the amount of heat generated is equal to the amount of work done by the external agency, that is equal to VI delta T. This is the amount of heat generated in a conductor when a steady current flows for a time interval delta T. And this is the equation for what is known as Joule's law. So H is equal to VI delta T. From here, electrical power can be determined as delta W divided by delta T, that is equal to VI. Electrical power P is equal to delta W divided by delta T, that is equal to VI. For an ohmic substance, what is an ohmic substance? The substance that obeys Ohm's law. For an ohmic substance, V is equal to IR, which implies the power P is equal to, so substituting V is equal to IR, this will give you I square R, or substituting I is equal to V by R, this is V square by R. Now finally we have three equations for electrical power. The electrical power P is equal to I square R, or V square by R, or simply VI, and the amount of heat energy. The amount of heat energy therefore can be written as VI delta T. This is equal to I square R delta T, that is equal to V square by R delta T. The last two equations are applicable for ohmic substances. Please be aware of these two. These equations are applicable only for ohmic substances, whereas VI is applicable VI is the general expression for electric power. Now, how to identify which equation to be used where? If V and I are provided, you can use the formula P is equal to VI. If I and R are given, you can use the formula for power as I square R. If V and R are known, you have to use the equation like V square by R. Okay, let us take a situation as an application of this concept that is related to power transmission. Power transmission. As we know, we are getting electricity from or through the public systems that we are having in our state. In Kerala, it is Kerala State Electricity Board or simply KSEB, that is in charge of delivering electrical energy to homes and other industrial institutions. Now, so we need to transmit power from one place to another. Okay. You have to understand that it has to travel a long distance for the power transmission to take place. Ready? Now let me consider a situation. I got a device of resistance R, and I want to send this much power to this device. Okay, so one transmission line gives power, a current I flows through this one, and this is the phase of the line and this is the neutral of the line, and these two are maintained with a potential difference V, or the potential difference available to the device is V. The power delivered to the device is P, the resistance of the device is R, the current through the device is, electric current through the device is I. So I can say P is equal to VI, where V is the potential difference experienced by the device. It is a potential difference experienced by the device of resistance R. Let RC be the resistance of the transmission line. RC be the resistance of the transmission line. RC be the resistance of the transmission line, which means I can treat the circuits together as this is resistance R, that is a resistance of the device. Oh, sorry, resistance RC, that is a resistance of the transmission line, and this is the resistance of the device, which is R. And the current in the circuit is I. Now, power wasted in the transmission line. It is given as PC. Power wasted is equal to PC. Let us take it as PW, as it is power wasted. By whom? By the transmission line. Let me say this resistance is RC, which means I can say power wasted is I square into RC, because these two are coming out to be in series. Power wasted is I square RC. RC is the resistance of the transmission line. But what is I? You have from this equation. I. V is the potential difference across this device. Since the resistance of the transmission line is generally small, this will be the potential difference between the between the phase and neutral also. Almost. Power wasted is I square into RC. But I can be written as P by V. This is P divided by V, the whole square into RC. That means power wasted is equal to P square RC divided by V square. Now what is P? It is a power delivered toward the device. P is the power delivered to the device. What is V? The potential difference between potential difference across the device, or potential difference between the transmission lines, phase and neutral. What is RC? The resistance of the transmission line. Here you can see that the numerator is a constant, which implies power wasted is inversely proportional to V square. The power wasted in a transmission line is inversely proportional to V square. V square. That means, how can we minimize the power wastage? What is the method of minimizing the power wastage? Method of minimizing power wastage. You can just see from this equation. Transmit at high voltage. Transmit power at high voltage and low current. If you look around you, okay, this is what generally we say. This is applicable for AC also. That is where I say in your localities you will find substations. 66 kV substation, 110 kV substation, 11 kV substation. The substations are there, and the power supply that we are getting to our home is just 230 volt. How is it possible? Okay, let us say from a 66 kilovolt power station, the signal is transmitted at 66 volt. Then it is using a step down transformer. It is converted into 11 kilovolt, that is to local substations. From local substations, the transmission line near us will have 11 kilovolt to supply, which will further reduce by another step down transformer to 230 volt, and the same is what is transmitted to our home. Which means 66 kilovolt. You can see when signal is transmitted 66 kilovolt, current will be small. When the voltage is reduced to 11 kilovolt, again current will be increasing. When it is reduced to 230 volt, current will be higher than, will be greater, which will be sufficient to manage the devices in our home. For long distance transmission of electricity, the energy is transmitted at high voltage. The purpose of transmitting at high voltage is to minimize the energy loss. I hope the same is clear to you. Thank you.